Hi and welcome. I'm Corey Kell, creator of FlatEarthIntel.com, and today's presentation we're going to talk about the 9-step geometric validation process using the sun to determine Earth's true surface shape. And with that, let's begin. 9 steps, and we'll go through them and then we'll get in a little more detail on each step. Step 1, identifying the equipment. We need to know what equipment we're going to use to perform this observation and test, and when we test Earth's surface shape. Step 2, ID test location. We need to know our test location, whether we're in the northern hemisphere, southern hemisphere, or in the tropics. The closer we are to the sun, the more evidence that's going to tell us as far as when the sun gets to its apex, whether or not we're measuring from a flat or a spherical curved surface. Step 3, sun survey point. And we're going to show you how to set up a sun survey point using what's called a Marks device, and that sets the geometric edge to begin the process. In other words, there are 8 doing the 45-degree sector test. There are 8 sectors, so we're going to test sector 8, or sector 1 and sector 8 in the 45-degree sector test. And that creates countability. Step 4, the OS station setup. And we're going to show you actually how to set up the orienting station, what that entails. Step 9, orient the orienting station. OS being the orienting station. You orient it basically using a compass in a direction to the sun. And again, our first reading is going to be a westerly reading, and then the second reading is going to be easterly reading the following day. Step 6, identify the 2 timing procedures in which we're going to what we're going to use. Time set and sun plot. We'll go through each one of those. Step 7, actually measure the sun's height or vertical angle, the technical term. Step 8. Working the test box, using the test box worksheet, really a creative tool for using it, and then going right into the right triangle calculation, which is basically you're using a right triangle calculator. So if you use a calculator, you can do that. It's very simple. And then the last step, step 9, record all data for record. So those are the 9 steps in the geometric validation process using the sun to determine Earth's true surface shape. Let's start with step 1, and this is the equipment. Gather all the equipment. And what we have here, item number 1 is a whiteboard. It's roughly about 13 inches by about, I think, 6.5 or 7 or 9 inches. And a whiteboard is, I use a whiteboard because it's easy to write on. When you're out there doing the testing or observations, you can write all that data, date, time, group, sun height, and azimuth to the sun right there on top of the whiteboard. So very effective item to have within that. Item number 2, which is the actual digital protractor or the angle finder. We'll talk a little bit more about that in the next slide. Item number 3 is the tape measure, which is in feet and in meters. We set our OS platform height to a 1/2 meter. You want to be closest to Earth's surface for accuracy. Measuring it right from the surface of the Earth. Item number 4, the sun shield. Always use eye protection, sun shield, and sunglasses or protective lenses. Item number 5, the marker for writing on the whiteboard. Item number 6 is a plumb bob. Plumb bob, you're gonna that's on a string. You're going to dangle that right over the radial arm of the digital protractor. Right over to the sun survey point, and you want to make sure your plumb are close to that survey point for accuracy. Item number 7 is a tri-level, and these come in different forms. This one here is a tri-level. You can use a T-level, and you put this right on the OS platform to make sure you're cross-level. Item number 8 is a metal, this is a stake for the sun survey point. This is for use in rocks and hard surfaces. You can use a bottle cap, a penny, a golf tee, a plug, anything that you can put in the ground, depending on your surface, just to mark it through the Marks device, and I'll talk a little bit more about that later. Item number 9, this is the cross level. This is you put on the Marks device. You lay that cross level. You want to make sure the Marks device is cross level. Item number 10 is the lens-edit compass, and this has 2 scales on it, degrees in red, and mils or milliradians or millirads in the black scale. and there are 360 degrees and 6 400 mils in a complete circle. 17.81 mils in, or 17.8 mils in 1 degree. Item number 11 is the tripod, which you're going to mount or hold up that OS platform. The additional list is of course, the Marks device, what I talked about. And this is basically an 18 by 24 inch long piece of wood by about 6 inches wide with a center hole cut in the center. And this is where you're going to put your survey marker. And you put 2 screws or nails, 4-inch long nails or screws, and put that about 2.5 to 3 inches above the surface of the wood, and then mount a string line going right down the center line of that. And that sun's going to create that shadow once it's center line on there, and then that's your solar noon to that. This is what's called the Marks device. This was named after a Latvian Special Forces first sergeant who helped me make the device. We made it in his workshop. Item number 13, sunglasses. I said always use eye pro. Double eye pro, you have the sun shield and sunglasses or eye protective wear. Dark lenses. Again, even if you're viewing the sun just in a very short period of time, you always want to protect your eyes. Item number 14 is the manual protractor. You want to verify the digital protractor by using a manual protractor, and we'll show you how to do that. Item number 15 is the stabilizer board. And you put this underneath the OS station, and that helps shift the entire OS station if you need to shift it on an azimuth. It makes it much more easier. Let's talk about the digital protractor. This one by Neotech. It has a range from 0 to 225 degrees with a 0.5 degree accuracy. When I tested it against a manual protractor, no difference. Exact same reading. And here we have the display window, and of course you have a control panel light which illuminates. That runs off a 9-volt battery and has several level vial bubbles on it. The radial arm, again, this moves. You lift this or move this top guide rail, which is the measuring arm on the digital protractor. And this is where you put the plumb line and the plumb blob right over the orienting station, over the sun survey marker point. Very easy to use item. Verifying the angle finder, again, just simply verifying it. Put a 45-degree angle on a large piece of whiteboard, and then place the digital protractor on there and just see what you get for measurement. It should be within a half a degree or right on. And mine was 0 degrees. It was right on. There was no difference. So you want to do that prior to using that device, just to make sure. Step 2. Know your location, ID your location. In other words, when I did my testing, I did it in the northern hemisphere here in the United States. It was Fayetteville, North Carolina, and then in Afghanistan, Kabul, Afghanistan, on the eastern side towards Pakistan, to an area called Poli Sharkey. But you can do this testing down in the southern hemisphere, and then of course in the tropics where you're closest actually to the sun. So the reason we need to know that and the time of testing is you want to test during the summer sun season when that sun is at its apex to you and it's closest to you, because then it's going to it can't be camouflaged. The surface, Earth's surface, can't be camouflaged by distance, and distance will help camouflage whether you're reading a flat or curved surface. But once that sun gets closer to you during that summer, it can't do that. It can't camouflage. It's going to identify itself then. Then it will reveal itself based on your angle. If you're reading, get readings over 45 degrees for the 45-degree sector test, you're measuring from a flat surface, not a curved surface, because you can't obtain that angle from a spherical surface. It's just too high. And again, we need to know our location to help delineate that, help give us the answer to that. The step 3, probably one of the most important parts of the whole process, the sun survey, setting up the sun survey point. And when I went into a 5-hour conversation with a professor of science, this was kind of a point of contention. He didn't want to kind of concede the sun survey point because he knew it was accuracy. Now you create accountability. In other words, you're setting that geometric edge between if you're doing the 45-degree sector test between sector 1 and sector 8, it creates accountability within the system. There's no room for wiggle, and science doesn't like that. And he had to confess, and I know he didn't want to really, but he did. And that let's credit him for being honest. He said, Corey, what you've created here is a very accurate process. So again, science agreeing that it was a very accurate process. And the sun survey point creates accountability. In other words, you're setting that geometric edge. This Marks device is oriented on magnetic north, on the line of magnetic, and you use a cross level vial. And then you can see here, this one is center line of the sun shadow. This is solar noon, what solar noon looks like. And then you simply put a marker in that hole, and that's your sun survey point. Now you're on manual linear alignment. And kind of what that looks like. You're setting that geometric edge, the line of magnetic. You're on that. You're now have created accountability. You're in this sector. Now you're going to test this sector across the sector at 3 hours or the designated sun plot time. And again, what it does is you've created accountability in that process. You're testing sector 1 and sector 8 in those 45-degree sectors, in those 8 45-degree sectors. Again, that's a huge win in the whole for the whole entire process. It creates that accountability, and that's what heliocentrism, when I looked into it, failed. It failed on the accountability process. Step 4. The OS station's orientation setup, and basically all you're doing is you're setting it up on a tripod over on the stabilizer board. You put that stabilizer board, connect your OS platform to the tripod, and then I mount my manual or my digital protractor using tape on there to help stabilize it in windy conditions. So it gives it more stability. You don't want that thing falling off like in windy conditions. And then all you're doing is orienting that towards the sun, whether it's westerly for your first reading or easterly the following day. Again, nothing too difficult though. It's a very simple process. And of course, your radial arm, you're over that sun survey marker. That's the oriented survey marker, sun survey point. Again, very simplistic. And again, there we put our tri-level on top to make sure we're level on our platform on top. So that's what it looks like. And then once you do that, step 5, you orient that towards the sun. What I'm doing, this is just an example indoors. You just orient that entire, and what you do is you shift this stabilizer board. All you have to do is shift it, and you run that azimuth right down that top radial arm, and to get your direction. So if you're doing it easterly, you're doing it towards the east, or if you're doing westerly, you're doing it towards the west. So very simple, very easy to do. Step 6, the 2 methods of timing: time set and sun plot. Time set, we'll talk about timing 3 hours from solar noon, so that's time set. So if your solar noon, the next example is 1300 hours, your first reading is going to be a westerly reading. Why? Because 3 hours, 3 times 8 is 24, 45 degrees is 360 degrees for that radius, for that orbital rotation for the Earth. So your first reading is going to be at 1600 hours, and then you're going to measure that azimuth and height to the sun and get that reading. Easterly reading will be the following day at 3 hours prior to solar noon. So again, if it was 1300 hours, your solar noon or your morning easterly reading time would be 1000 hours. And this is time set. It's at a set time when you're going to do it 3 hours. Again, testing that 45 degrees sector. The other one, the next one, timing is sun plot. Perform a sun plot, which is a designated azimuth from the OS to the sun's position in the tropics. Example, 267 degrees grid azimuth, that's map azimuth, or what we're doing digital mapping. That would give us 45 degrees. When we do it on ground, we have to add 9-degree declination, and based on our location, that would equal 276 degrees magnetic, or using a compass, what we orient the orienting station on. And that's for a westerly reading. Easterly reading would be the following day. A grid azimuth at 99 degrees, or 90 degrees grid azimuth, plus a 9-degree westerly declination would be 99 degrees magnetic. So we'd go measure 99 degrees magnetic using a compass, orient that, set that radial arm up, and wait for that sun to come center mass. That's all we do. That's sun plot. And that azimuth will determine if you're correctly on the sun. It's based on the globe model's distances on its latitude and longitude. So again, you can't get around that. That's accountability within the system. And here's what the sun plot looks like. And this globe, digital globe, is Google Earth. One of these latitude and longitude squares is 10 degrees. Remember, on the globe model, distance equates to what? Surface angle. So we're doing 45 degrees, so we do 4.5 squares. You want to make sure you're at least 4.5 squares. In some instances, we're a little bit more, but we want to make sure we're at least 45 degrees. So here we run easterly 90 to 113 degrees, and this runs all the way from the Tropic of Cancer in the summer solstice to the equator. Same thing in the westerly, 267 to 244 degrees. Again, very telling, and this again is part of the accountability within the entire process. You can't get away from these azimuths because that's what you're using when you're measuring it based on the globe model. Again, and this is where we found fault within the globe model. Step 7. Measure the sun height. And when we actually measure the vertical angle or the height to the sun. And again, this is what the sight picture looks like, and I'll give a little blow up of that. That sun center mass of that radial arm, digital protractor arm center mass. And that's what it looks like. In this model, we had like a little window. There's a 2-minute window, call it for easterly reading, where there'd be a 2-minute window just prior to 2 minutes to that sun coming center mass. And on the outside, this is kind of what it looked like on the side along that top rail bar. Again, the sun center mass, you want to make sure your OS is plumb and it's level. And remember, when we're doing that, we get sight picture center mass of the sun. You have angles above the sun and angles below the sun. Again, the sun being always 90 degrees in its location on Earth, whether it's the flat Earth or the globe model. Basically, kind of the kiss of death for the globe model. So, again, very simple, nothing very complicated about it, really. Once you understand the process, it's a very easy process. Entire process is very easy. Once we get that angle, and I'll show you an example of that. All we're doing is we're adding the vertical angle or the sun height here for the globe model plus the observer angle or the distance. So if we're doing 45-degree sector test, we put 45 here. And then if we get a sun height, let's say at 50.1, we add 50.1 plus 45. You add those two numbers together equals 95.1. The sun being 90 degrees, so that's 5.1 degrees over. That exceeds the globe model's limit. That's for the globe model. The flat Earth model limit test box looks like this. The sun height plus the observer angle. The observer angle is always 0 degrees, so you add 50.1 to 0 degrees. It's 50.1. That's a pass easily for the flat Earth model. Flat Earth model having a huge advantage. Let's take a look at the right triangle calculator because that's what we got to go to next. Very simple calculator, and you get this at righttrianglecalculator.net, and then go to Right Triangle Calculator, click on that, and it's going to put it all up at Right Triangle Calculator. Remember what we got on our reading? We said 50.1. We're doing the 45-degree sector test here. We add those two numbers together. That's 95.1. The sun's limit, 90 degrees. We're 5.1 degrees over. We take that number and we come up here and we add that into angle A, 5.1. And then for distance, we give the sun's distance from the Earth, 93 million miles we put here. Then we put those two in the right triangle calculator and we hit calculate. That's going to give us the answer right here to number A. 5.1, the angle 1, and then answer will be right there in angle A, which is 8,300,000 miles. So if that number is larger than the sun size in heliocentric model, that means you're no longer looking at the sun. You are off the sun. In other words, you failed. That globe model fails for that model, and it fails by a lot. You're in another heliocentric galaxy. Again, that's a huge failure. That's such a 5.1 degrees. That's such a massive failure. Just to put it in perspective, that would be like your high school football team going into professional football the first season and winning the first 3 straight seasons of the Super Bowl in an undefeated record. That would be putting it in perspective. That's how massive of a failure this is. Step 9, record all data for record. You're going to put date. The date you did the testing or the observation, the location. You can use GPS or latitude, longitude. Time of observation, very important. Sun height, 0.5 meter. Azimuth to the sun, the direction your orientation station was oriented. And then the OS platform height. And then the elevation you did the test elevation is very important. And this completes the 9-step geometric validation process, testing Earth's true surface shape using the sun. I'm Corey Kell, creator of Flat Earth Intel. Thanks for watching.